Hello, everyone, and welcome. Thanks for joining us. We're going to get started here. My name is Jason Dornbos, and I'm the Marketing Communications Manager at Extol. Today, we're going to be talking about how to save cost and weight with 3D printed end-of-arm tooling. Our presenter today is Andrew Roderick. He's the lead applications and sales engineer for our additive manufacturing group. Couple of things to point out before we get started. We're going to be recording today's session so that we can share it with you later in case you have to share it with anybody else or you missed something because you had to leave early or whatever. Now let's take a second and make sure everybody knows how to use the chat. It probably is open already, but if not, there's a little Q&A icon near the top right corner of the event window. Looks like there's a little question mark in it. In the bottom right-hand corner, once that's open, you'll have a place where you can type your name and then type your question. To make sure that that's working for everybody, why don't everybody go in there and say where you are joining from today. So go ahead and put your name and where you are in the chat, and we'll get that going. And then during the presentation, if you have any questions, please feel free to put them in there, and then we'll make sure we hit all of those either at the end or during the presentation. Now, Andrew, would you like to take it away?
Absolutely. Thanks, Jason. Welcome, everybody. I'm excited to be here. Good morning, afternoon, or evening to wherever you're joining us from. Looking forward to a great conversation today about opportunities that can be realized by each of your companies. And as we go through the presentation, like Jason said, feel free to put those questions in there and we can answer them along the way if they fit in, or at the end, whatever works best. So without further ado, let's get started. For those that don't know, Extol is an engineering and innovation company that improves the way plastic products are made. We're located in Zeeland, Michigan, so right along the coast of Lake Michigan. For some context, Extol supports our customers in 3 different areas of our business. Plastic assembly technology, so you can think of heat staking, hot plate welding, spin welding, laser welding. Those are all technologies that have been developed and produced at Extol. And then another portion of our business is custom automation. So from robot cells to palletized automated lines to standalone assembly equipment. And then in the engineering services, this is where our additive fits into play. So our digital development center is where all of our additive initiative or service to our customers takes place. We have 3 HP Multi-Jet Fusion 5210 printers. We provide design support for our customers. We provide parts as a service from prototyping to production. And then we have post-processing, part finishing, and along the way, we use our innovation process to help our customers develop high-value applications. So there's a unique value to our customers when we look at why additive and why Extol. It's that combination between our plastic assembly expertise, additive manufacturing, and our innovation process. So we're going to take a quick look at the multi-jet fusion process for those that are unfamiliar with it. It's a relatively new technology that brings new innovation as the additive space with production as the end game. It's a powder-based system that utilizes agents to assist in the thermal processing of IR energy fusing the parts together. So some key benefits, consistent print times, part density and durability, and then they're thermoplastic parts that can be joined with traditional welding technologies. So the basics of multi-jet fusion, it starts with a layer of powder. It's 3/1000ths of an inch layer of powder that's spread across the build surface. And then HP's leverage their 2D printing and they apply 2 different agents, a black fusing agent and a clear detailing agent. The black is applied where you want the parts to be grown, and the clear is applied around the edges of those parts. Then when IR energy is applied, the black fusing agent absorbs that energy and melts the plastic, and the clear evaporates and through evaporative cooling gives you a nice boundary layer between the fused and unfused plastic. And after that, you have a fused part, and the process continues for thousands of layers until you get to your final build height. One thing to note is it's a build envelope. It's not just a build surface, so you can nest and position parts throughout that whole three-dimensional box that you're seeing on the top right-hand corner there. Another thing to note is the IR energy penetrates 2 to 3 layers deep, so you're getting really good molecular entanglement and basically mini welds happening between the layers, giving you great X, Y, and Z strength. Xtol currently offers 3 different materials for the multi-jet fusion process, PA12, BASF TPU, and the newly released polypropylene. Xtol was the alpha development partner with HP and has been printing this material for the last 8 to 9 months. So when we look at the different materials, there's different aspects or different key features why you would use those for each individual application. PA12 is great for parts that require a strong, rigid material, increased accuracy and tighter tolerancing. With PA12, this is our most dimensionally stable material. It also does very well with fine detail, and then it's more temperature resistant than all of our other powders. BASF's UltraSynth TPU unlocks some new applications with its unique characteristics. It's a flexible, durable material, shock absorbing, soft touch non-marking. We'll dig into that deeper later in the presentation. And then the ability to design controlled stiffness and durometer through latticing. Polypropylene is an exciting new material. It's real polypropylene. It's not like polypropylene-like or, like you see in a lot of other technologies. This is tried and true polypropylene. It's lightweight, the ductility, elasticity, and toughness, great chemical resistance. And then the weldability, with polypropylene being one of the most common plastics in the world, there are a lot of opportunities for welding multi-jet fusion polypropylene parts to injection molded materials that are chemically compatible. This brings functional prototyping to the next level. So we're going to start by taking a look at a couple use cases that HP has published before taking a deep dive into the benefits of multi-jet fusion printed end-of-arm tooling. The first use case is a machine arm from an industrial paint machine. Multi-jet fusion provided the strength needed to enable this application with 3D printing components where other technologies fell short. They were able to achieve lighter weight, enabling faster movement and more precise control. They produced chemically resistant, strong, durable, and detailed parts. And then there was also benefits in eliminating inventory needs, as well as the smaller arm led to significant savings. The second use case is more of an organic contoured shape with the unique benefit of integrated vacuum lines. There was a huge weight reduction of 87% over CNC machine parts, and the weight savings realized with printed end-of-arm tooling could enable the use of collaborative robots, which seem to be an industry trend in several applications. So another way to unlock cost savings by reducing weight. Each application is very unique, so we will use this demo end-of-arm tool to highlight the different benefits of multi-jet fusion and look at some design tips. So let's take a closer look at the end-of-arm tool in action. You'll notice when I start the video, there's 2 different methods of picking up the handles in the printed nest there. There's a gripper fingers on the right and then vacuum cups on the left. So when we look at the different subsystems, just want to highlight a couple: integrated clips for pneumatic tubing, soft touch grippers, so this is the TPU material we'll look at, integrated vacuum plumbing, so lines printed into the part, and then lightweighting capabilities there. And the robot doing a nice little dance for us. So there's 3 different subsystems I want to take a closer look at. Let's start with structure. So the structure of your end-of-arm tool is where the weight savings and design freedom begins. The combination of plastic being lighter than aluminum and the flexibility of putting material only where necessary can unlock huge benefits. When we look at mounting, limitless mounting options, so any angle, any compound angle, those things become easy when you're starting from scratch with a 3D printed component that allows much more design freedom. When you look at the different materials, I'm going to come back to generative design, but when we look at the different materials, PA12 is you're strong and rigid, but if you really needed a lighter weight, polypropylene might be an option for specific structures. Generative design can drive down weight and higher end applications. So let's take a look at what generative design entails. It's an exciting tool for getting the best optimized shape and use of material to reduce weight while providing necessary structure. So when you look at this example from left to right, it's showing the journey from traditional subtractive manufacturing design to a topology optimized or generative designed design. When you look at all of the different steps along the way, not all applications require you to go direct to a topology optimized design. You might be okay just with a lighter weight design and not have to invest in the higher end optimization software needed for topology optimization. So when you look at, when you're going through the process of designing your part, you can stop at any one of these designs wherever you get to the point where you meet your requirements. The second subsystem that we can look at is pneumatics. With multi-jet fusion, pneumatics can become cleaner and easier to assemble. So let's take a look at integrated airlines. In this case, it's individual lines, but there's the ability to have multiple branches coming to a common fitting, reducing the amount of connections and pneumatic lines that you're running. When we look at these fittings, they were threaded into the PA12 after they were tapped after printing. But for larger fittings, you might be able to print in the threads or insert a brass threaded insert if required. And then thought out routing with integrated clips can also speed assembly and make your end of arm tool look cleaner and be a tighter package. Also along the pneumatics frame, it would be from my machine design background, it always seemed like there'd be a part that required vacuum in a certain location, but due to geometry, you had to settle for a subpar off-the-shelf solution. With TPU and MJF, custom vacuum cups are now a possibility. And then back to design freedom, you're able to place and orient vacuum in the right orientation without messing with several off-the-shelf brackets and configurations to get the desired compound angle that you need. The third subsystem is part handling. So the common adage of complexity is free with additive is true with custom grippers. The savings over CNC increases with the added complexity that would require multiple setups or even allow features that are not traditionally manufacturable. Vapor smoothing and the BASF TPU provide an excellent soft touch solution and can be combined with PA12 for applications requiring increased rigidity. So you can see there's two different train of thought here. For the top portion, it's all TPU, and for the bottom portion, for a higher requirement application, there was TPU for the soft touch and PA12 for the rigidity. And custom grippers can lead to allowing faster robot movement by securing your part more securely. The vapor smoothing solution that Extol leverages is from Additive Manufacturing Technologies. The AMT chemical smoothing process takes soft touch tooling functionality to the next level. It smooths the surface to reduce marking, seals the TPU outer surface, and makes grippers easier to clean to avoid dust and contamination from scratching your parts. So you can see an unfinished TPU sample on the top left there, and after vapor smoothing, you get a really nice smooth surface. And when I talk about sealing the outer surface, you can see the water droplets on the lower bellow part. So the key benefits of multi-jet fusion, I think, can be summed up into three categories. There may be more, but we're going to touch on these three. Design freedom, so we talked about the endless options for mounting angles and those sorts of things. Speed of optimization, iterations, ability to get your end of arm tool to production faster. And then weight savings is a large driver in lowering the cost of your overall system. So let's take a little closer look at lowering cost. Besides, being able to produce the actual tool cheaper, you can look at robot costs. When you take weight out, could you go to the next payload down as far as robot to save cost and overall the robot price? Cycle time can be increased potentially with more precise, faster movements, as well as decreasing the weight on your tool could allow you to have more action, such as cylinders attached, that would reduce robot movement and reduce cycle time in that manner as well. And then speed and accuracy of the robot movements could also lead to cycle time and cost savings. So that's all great. You may be saying, what do I need to consider when designing end-of-arm tooling with multi-jet fusion? So let's take a look at a couple different things to consider. When we look at part size, I mentioned that the build envelope is a three-dimensional space, and you can see the dimensions there. So when you are looking at your end-of-arm tooling design, we want to limit material to lower cost and weight. The more parts you can fit into this build envelope, the more cost-effective your end-of-arm is going to be. So, as well as optimizing your build volume. So if you can nest parts together or create such a design that nests together quite well, you can increase the amount of parts that you can fit into this build envelope. And if your end of arm is too big for this to be built as one in this build envelope, splitting parts is always an option. There might be attachment joining methods that you can put those parts together. Could be a through bolt with a nut, brass heated inserts, dovetail joints. Those are all things that we would be able to take a closer look with you on an application by application basis. When we talk about soft touch tooling design, we like to minimize the TPU that's used due to this being a little bit more expensive than the PA12. So in some instances, like the gripper fingers on the left, it didn't make sense because they were small enough as is. But for larger parts, like the fixture on the top, where you might have a riser or different things like that, we combine the TPU with the PA12 in a post-assembly operation. You might want to design a poke yoke for easy assembly. And then, as we mentioned earlier, take into consideration supported versus unsupported TPU. And that's definitely design dependent, whether you need that added rigidity of the PA12 backer. Combining the PA12 and TPU can be done with dovetail joints like you're seeing on the right there, fasteners, custom designed printed clip features. Those are all ideas and things that we can work through on your design. When considering vapor smoothing with the TPU, it is important to have a feature present to hang the parts from, as the vapor smoothing process requires parts to be suspended. So in the fixture case on the, or example on the left here, There's a flathead screw hole to combine these two pieces together, and we were able to hang that TPU cap from that hole. So some sort of feature. It could be sacrificial. You could just design a little loop that the parts can be hanged from, and you could clip that off after the vapor smoothing process. Integrated pneumatics. With multi-jet fusion being a powder-based process, ease of powder removal is important to consider in the design phase. For long, complex internal channels, it can be helpful to model a pull chain in CAD that is printed with the part, then pulled out during post-processing to loosen up the powder in these channels. So you can see that blue highlighted, basically pull chain or ripcord, is an actual cord that's printed with the part, and then we pull that out at the end, and that breaks up some of the powder, letting the glass bead blast media do a better job and get in there more efficiently. So to review, there are three main areas to consider when designing end-of-arm tooling: part size and weight for cost efficiencies, soft touch tooling for non-marking of your parts, and then integrated pneumatics to clean up and reduce weight with your part or your end-of-arm tooling design. And with that, I will turn it back over to Jason. Do we have any questions that have come in?
Great job, Andrew. Yes, we have a question, and for anybody else who's out there that still has a question, feel free to put it in the chat. First question that we've got is, how does robot cost and cycle time reduction translate to dollars?
Sure. Yeah. So we've seen customers identify savings of up to 100,000 per year just by, like I mentioned, maybe lightweighting an end of arm to allow more cylinders to be put into place. Better utilization of the robot by reducing cycle time. And then if you were to be right on the line with, a bigger robot versus a smaller robot and the different movements and different things like that, you could capitalize on savings by lightweighting.
Great. Also, does Extol offer assistance in designing end-of-arm tooling?
Yeah, absolutely. We do have design services that we would be happy to talk about your application and either help through design consultation and you design it, or we take care of the design for you.
Great. Is the print resolution high enough to screw in connectors easily? I think we're talking about the pneumatic fittings and stuff like that.
Yeah, sure. So resolution, when it comes to threads, anything under M6 or M6 and below is probably best to do just the tap drill size and chase the threads afterwards. But you have a high enough resolution for like M8 and above. I find that most of the time I like to have the tap drill size and just chase it with a tap post printing to get the best results. And also to think about, if you need higher torque, not necessarily for fittings, but heated brass inserts are a great solution for higher torque applications.
Are there any other questions out there before we close this off?
For the translated to dollars question, I'm not sure if I fully answered that. I said that our customers had identified savings, but in the application that we were looking at, or in applications, we've seen potential savings of 100,000 a year just in that increased cycle time efficiency. So I wasn't sure if I dropped that number or not, but just wanted to clarify.
Perfect. Well, if anybody has any questions after the event, feel free to contact Andrew. Andrew, do you have your contact details that you can share with people?
Yeah, absolutely. And I just want to make a point to design and development services. If you need prototype parts, those are all things that we can assist you with. So whether you need one part and it doesn't even have to be end of arm tooling. You know, if you need a part for prototyping of a project or something like that, definitely reach out and we can help you from you know, one part to thousands of parts.
Awesome. So as you can see, we've got Andrew's contact details on the screen there. You've got his email address, his phone number, and then also his URL if you want to connect with him on LinkedIn. You can type that in, or you can just search for Andrew Roderick and Extol, and you should find him. He's a pretty helpful guy, and I'm sure he's happy to help you with any of the questions that you might have. We'll also be following up with each of you after the event, and giving you the opportunity to download this recorded webinar. So with that, thank you everybody for joining us, and have a great day.
Thank you.